Hello friends, MoNaCo here with our sixth video in our moles and stoichiometry series. We're doing mole-to-mole conversions today, and that's going to involve using the balanced equation to make a ratio that we solve using cross multiplication. So we're going to be able to convert between moles of one compound and moles of another compound using that balanced equation as a guide. The reason why we do this is because compounds react in very specific ratios. Balanced chemical equation shows us those ratios, and we can use those ratios to do things like predict how much product or how much reactant would be used in a chemical reaction. It's basically like kitchen chemistry that you're using to scale up or scale down a recipe that you have. Okay, so here we are. Chemical equations like that recipe, where the coefficients tell us about the reactants and the products that we need in order to make the recipe work. Reactants in an equation are the specific ratios to produce a specific amount of products. You can only make a peanut butter and jelly sandwich if you have 2 pieces of bread or whatever it meant. If you run out of bread, the ratio is not right. It's not really technically a proper sandwich. So in the scenario of cooking, we're talking about maybe making a batch of cookies. 3 eggs, a cup of flour, 2 cups of sugar makes 24 cookies. We chemists like to abbreviate those into symbols, of course. So 3E plus 1F plus 2S makes 24C. Now, if we were to mass the eggs and the flour and the sugar beforehand and the cookies afterhand, we should have the same amount of mass before and after. It's why we balance the equation to show that conservation of mass, the law. Well, what happens if you were to take that same recipe for 24 cookies and you had to make 48 of them instead? You might think, well, I'm just going to double my recipe. And you would be right. But sometimes that's not going to be so simple. You're not just going to be doubling or having a recipe when we're talking about chemical equations. We might have a funky ratio, or we might have one ingredient that we run out of first. So if we're going to properly solve these types of problems, we got to set up proportions and solve them. These are very straightforward, but you got to have a lot of practice at it. So in this same problem, we want to make 48 cookies. I'm going to put a C in there. But the recipe only calls for 24 cookies. And we're asked how many eggs would we need in order to do this. Now, I always put my given in the bottom, in the denominator. So given from the equation always goes in the denominator in these proportions. If you don't set it up that way, you're not going to do it right. So what we've got here is we've got an x. We don't know how many eggs we need. But if we solve for our proportion now, we got 24x because we're cross multiplying. 24x equals 48 times 3. That's 6 shy of 150, 144. So if you divide both sides by 24, x ends up equaling 6. 6 eggs that you would need if you're going to double your recipe. And now that's pretty intuitive. You have to double your recipe, and the original called for 3. I'm going to use 6 this time. But they get a little more complex than that, and we stop talking about ingredients in food. For example, if you have 10 eggs and an infinite amount of sugar and flour, meaning like you got a giant bag of both, how many cookies can you make? Well, we take our original equation and we look and say, okay, well, we're going to relate 10 eggs, what I'm given to in the problem, to the number of eggs that the problem asks for, to X cookies, as the recipe is to 24 cookies. And then we go ahead and cross multiply and solve our proportion. So we've got 3x equals 240. Now when you solve for x, dividing both sides by 3, you get x equals 80. X equals 80 what? 80 cookies. So if you had only 10 eggs, you could make 80 cookies. It's kind of why we do this ratio. To solve for how much you'd get out or how much you'd put in or how much is consumed, what can we make, how many cookies can you make if you're limited by one of your ingredients. So we use this process for balanced chemical equations. If you don't have a balanced chemical equation when you start to try to do the ratio process, you're not going to get the right answer. So always check to make sure that equation that you're starting with or given is balanced. 9 times out of 10 it will, unless it's a multiple part problem. So question here. How many moles of nitrogen gas, N2, would be needed to produce 10 moles of ammonia, NH3? Well, the way we start out is we set up our blank proportion. And we have to relate ammonia to nitrogen gas. So N2 is what we got to get. We got to get N2 over in the top right corner. Our problem says that the N2 from the equation comes in ones, 1 mole of N2. Now, we produce 10 moles of ammonia, so 10 NH3 on the left, and the problem calls for 2 NH3. So again, I take my equation values given from the equation and the problem on the left, and we're going to solve for the x on the right. Cross multiply. So we get 2x equals 10. If you solve for x, both sides divided by 2, x equals, well, 5 N2s. And that would be how you solve a problem like this. Now, the hardest part is going to be setting up that ratio properly. Remember, the denominator gets the values from the mole coefficients in the balanced equation, and the numerator on the left gets the given number of moles from the problem itself. Let's get a couple more examples here. Balanced equation. Let's set them up and see. If 12 moles of C3H8 react completely, how many moles of H2O are formed? Well, we start by setting up our blank proportion, and we're relating C3H8 to H2O. So how many moles of H2O are formed? So we got X H2O on the right top side. The problem says that 4 is the H2O value. The problem that we're given is 12 C3H8. So we got to look for, and that's 1 C3H8. So when you go ahead and solve for X in this scenario after doing your cross multiplication, you will have C3H8 as your answer. I'm sorry, H2Os. H2O is what we're looking for here, because those are those units right there. So you're going to relate the answer through your cross multiplication. I want to see you do that for your full credit. I'll help you set up number 2 and 3 here as well. So if 20 moles of CO2 are formed, how many moles of O2 are reacted? Well, set up your proportion. We are O2 is our interest, so we got XO2 of interest on the top right side, 20 CO2 on the top left side. So we look for our problem, 3 CO2 on the left-hand side, and O2, 5 O2 on the right-hand side. So when you solve for X, we are going to be solving for O2s, and you find out how many moles of O2 will be needed. The third scenario here, set up our blank proportion. We are given 8 O2s completely. 8 O2 starts on the top. How many moles of H2O are formed? H2O is the X. How many moles? H2O. So then we go back to our problem. We're relating oxygen to H2O. So 5 O2s is related to H2O because 4 H2Os. So when you solve for X in this scenario, it will be in the units of H2O, moles of H2O. Setting up the proportion is the hardest part because cross multiplication is really easy. So set up your proportions before you go ahead and just try and solve the problems. Again, proportions are the first thing that you do. You set it up and then you solve it. Okay? The hardest part is knowing that your X value always goes in the top right corner, and then you have to read your problem for comprehension to see which values go where. The given value always goes in the top left. I strongly encourage you to put in your units, which are the species or the compounds. And that way you will be able to find out how many moles I know this because I'm looking for the how many moles, how many H2. So you got to read your problems to set up the numerators, and the denominators you got to read your balanced equation. Okay? So set up these proportions and solve accordingly is what I expect to see for full credit. A lot of practice on this stuff because it takes some attention to detail. The basics of molar ratios have been shown to you, and now you just got to practice, practice, practice. Thanks for watching.